Hi, my name is Niklas Hohmann and I will be talking about how changes in sedimentation rate affect different types of paleontological data. A prime example for the effects of changing sedimentation rates are shell beds, because every shell bed can be either explained by a biological process, which is that there's more shells being placed in the sediment, or by a sedimentological process, which is that there's less sediment in between the individual shells, which creates this condensation. In this video, I will focus on two different sedimentological patterns and examine how different data types, specifically rates and point measurements, change throughout this sedimentological gradients. The first sedimentological scenario is just given by a sedimentation rate that changes through time from a high sedimentation rate to a low sedimentation rate and back to a high sedimentation rate, which could just be an ordinary sedimentary sequence. This sedimentation rate creates an outcrop that is 10 meters high, and here you can see how the time correlates with the outcrop observation. What's obvious is that the time intervals with high sedimentation rate form most of the outcrop, whereas the time intervals with low sedimentation are just like a very, very tiny part of the actual outcrop. Looking at this from a condensation perspective, we see that the time intervals that are deposited with a very low sedimentation rate are highly condensed, whereas everything else is strongly diluted. So everything that is deposited with a high sedimentation rate is diluted. Everything that is deposited with a low sedimentation rate is condensed. The first data type I want to look at are rates. So that could be, for example, first or last taxon occurrences, shell abundance, or essentially whatever ends with per time unit or per stratigraphic height. And here I have an absolute null hypothesis, a rate that does not change through time. But if we translate this into the outcrop observation, something really curious happens. And that is that again, in the time interval with a low sedimentation rate, we get an extreme condensation of this rate, whereas in the time interval with a very high sedimentation rate, we get a strong dilution of this rate. And this will affect first-last occurrences equally as well as shell abundance. For the shell abundance, for example, this pattern of condensation would be a shell bed, as I showed in the very beginning of this video. The second type of data I want to look at are what I will call point measurements. So these are simply measurements that are taken in time or at a specific outcrop height or a core depth. And this could, for example, be isotopes, climate variables such as temperature, whatever you want to measure. And here I have a slow change with a slow oscillation. And if this is translated into the outcrop, you can see that at the time intervals with high sedimentation rates, this oscillation is being stretched, whereas in the time intervals with low sedimentation rates, it is squeezed together. But the original values are not changed, which is a stark contrast to the rates. So for the point measurement, you will always observe this squeeze box effect. The values remain unchanged, but they're like squeezed and stretched. Now I will look at a second sedimentological scenario, and that is that we again have changes in sedimentation rate, but this time this includes erosion. So there's a time interval where there's only sediment removed, and important, there's also a time interval where we first have a deposition of sediment that is then removed afterwards. And this will remove a large part of what was originally deposited and will generate a hiatus in the outcrop. The curious thing about hiatuses is that there's no general pattern about the sedimentation rate or the condensation below the hiatus. but above you will always see a short condensation interval, which is simply because the sedimentation rate transits from a negative, from erosion, into a positive deposition. So it will always have a short interval with low sedimentation rates that creates this condensation above the hiatus. Now again, looking at the rates here for shell abundance, what is important in the presence of hiatuses, the model I'm presenting will not work for first to last occurrences, which is simply because they're defined post hoc in the outcrop, so there's no general statement that can be made about them. And here, just as expected, a large interval is missing, and there will always be this condensation right above the hiatus, but no general statement can be made about the rate right below the hiatus. Looking at point measurements, this looks a bit different. So here it's the same oscillation and increase. And because there's a large slice of time missing, we will observe this potential jump around the hiatus, followed by a slight faster oscillation that is generated by the condensation above the hiatus. So this is how the two major paleontological data types that are rates and point measurements behave under changes in sedimentation rate and hiatuses. And to fill these a bit abstract examples with some meaning, let's put them together. So let's assume that our rate are first or last occurrences, blue is the sedimentation rate, and black is some climatic variable such as temperature in this case. So assuming we have a constant origination and extinction rate and a slow climate change. And if we don't incorporate information on the blue curve, the sedimentation rate, we will get a very biased impression from what we can see, the outcrop or the core. So between A and B, we'll observe a relatively stable climate with low biological turnover, whereas in the short condensed interval between C and D, we will observe a rapidly changing and oscillating climate accompanied by a rapid biological turnover. And this is really why it is important to incorporate sedimentological information into paleontology to get a proper development of time throughout your core and your outcrop. The model I used to create the plots I showed before is also available as an interactive web application, which is called the Shellbed Condensator. It provides some background information, and if you click on Get Started, you get this interface where you can change shell input and the sedimentation rate. For example, I can create a erosion here, and then it will show the stratigraphic expression, so what can be observed in the outcrop here with a hiatus, and you can see the condensation right above the hiatus. And if you're interested, you also get an age model where the time interval that was eroded is marked. And it will respond live, so you can just play around and see what happens to get a feeling for the different effects I have displayed before. If you want to have further information about how this model works and how you can incorporate information about sedimentology into your own analysis, there's the link for the app you can just play around with to get a feeling for how the different effects play out. Then the publication where the model is published is available in Paleos. The model itself is also available as 4R in a standalone package, which you can download on CRAN. And if you want to see an example of how to reconstruct sedimentation rates and age models in deep time, then you can check this example by my colleague Emilia Jarochowska. And you can just scan these different QR codes on the site to get a direct access to these publications. And if you have any more questions, my contact is either on the app or at the beginning of this video, and I'll be happy to answer any questions. Thank you.